All right. Now it's my very great pleasure to introduce Dominic and Kate, who are going to talk about opening closed systems with GlitchKit. They brought a bunch of interesting looking electronics with them, and I'm very curious to hear how they are going to help us liberate all our devices. So please give a warm welcome to Dominic and Kate.
Thank you. Yeah, there we go. Everyone can hear me. All right, I'm Dominic. This is Kate. These are our faces and Twitter handles if you want to, I don't know, live tweet about how terrible this is. I work for Great Gadgets, and mostly I work on software and firmware for embedded devices, things like HackerF, GreatFet, Ubertooth. Do you want to explain who you are?
Hopefully my microphone's working. Perfect. So I'm not really in the InfoSec scene. I'm more of a reverse engineer. So I maintain projects especially that let you get more information about systems and see inside them. I especially love things that help people to learn about different systems and kind of get a foot in the door in various things. Face dancer, for example, is something I maintain the newer version of, and that lets people get their fingers into USB. GreatFet we both maintain, and that's a multi-tool that lets people get their fingers into all different kinds of things. So we're coming at this talk from a perspective of people who really, neither of us really are InfoSec people. I think you say you write software for a living.
Yeah, exactly.
I do reverse engineering, which is kind of on the periphery of the core, like hacking culture kind of thing. And really what we're here to talk about today is a tool that we built that helps people do things like reverse engineering and learning about systems more effectively. So
yeah, mostly what we build is interesting tools to open up things, and then we rely on the idea that other people will pick up those tools and do really interesting security things with them. So naturally, if we want other people to pick up our tools, it seems to make sense that we make most of them open source and available to people. And in that spirit, we'd like to thank a couple of people up front. Michael Elizabeth Scott, Scanlime. She does some fantastic reverse engineering work and is very good at explaining things. If you haven't seen her streams and YouTube videos and things, you should absolutely check them out. And there's some stuff in this presentation that was directly inspired by her work. Colin O'Flynn has done an awful lot of really interesting glitching work and taught people about that over the past couple of years. And also, we should thank Great Gadgets because they do enable us to come and attend events like this and spend our time working on these things.
Right, and so in this talk, we're not really the brilliant people doing anything that's absolutely earth-shattering. We're not coming up with new, techniques that enable you to sit on the cutting edge of science, but instead we're tool builders. We build things that let you do cool things. And so we kind of have the foundational people who have, kind of started blazing some of these paths forward, and we're building on a lot of their work. So
yeah, and I mean the reason that the first two are listed as people who are smarter than us is I actually tried to pick up Colin's work, and it's fantastic. His Chip Whisperer is really cool, and the software is kind of great. And I knew nothing about glitching, and I think we got into a conversation about this stuff's really cool, but wouldn't it be great if someone who's not a genius, like someone like me, can pick it up and glitch a system. And so that's kind of where this project came from, is just trying to make those things just a little bit more accessible, a little bit easier for everyone to use. So let's
Right, and a lot of this came out of conversations with those first two people, so it's really awesome. I really appreciate the foundation they built. So kind of give you background for why we're doing this kind of thing. This is the circuit board for an HDMI switch. Nothing super special about it, other than the fact that I was using it a few months ago, and it was it had an incredibly irritating flaw in that sometimes when you're doing something like playing a video game or watching TV, it would sometimes flicker on and off. And so naturally I did what anyone does when their electronics stop working, and I took it apart, figured out what the problem was. In this case, it was all the little signals, the hot plug detect signals that tell you whether their HDMI cables whether those cables are present and plugged in. The signals that indicated presence actually had a little bit of noise on them, and the system wasn't properly compensating for that noise. So every once in a while, a port that didn't have a cable plugged in would suddenly see a cable for just a split second, and it would try to automatically switch over to that input. And this device happens to be driven by an Intel 8051 equivalent microcontroller, a derivative microcontroller. And if I had the firmware for that microcontroller, it would have been probably 10 minutes of work to put a little bit of debouncing, put a little bit of noise filtering into that system and be able to fix this and have this work. But without the firmware and without this kind of thing, it's the kind of thing where you have to start off by rewriting the firmware from scratch, or coming up with some other hack, some analog filtering in order to make this thing work. Or as I did, buy a slightly better HDMI switch.
Yeah, sometimes the solution is to build a glitching framework, and sometimes the solution is to spend $50. And I'm really pleased that you chose both.
Here's another device that I was messing around with a little while ago. This device is the inside of a thermal camera. So it's the FLIR 2G165. It's a relatively inexpensive, something like 200 or 300 USD thermal camera. And it's actually a really cool piece of electronics. It's got an SD card, micro SD card that it captures pictures onto. It's got a USB port that it uses only to upload those pictures to computers. And then it's got a pretty powerful, pretty large microcontroller on there. And it would be really lovely to use a board like this for all kinds of experiments where you could take in thermal data and pass it to a PC. But the designers of this didn't really think about that use case. They didn't identify that as a use case they were interested in. And so despite the fact that you have this giant microcontroller with 512 kilobytes of flash, of which it was only using something about 100 kilobytes, without the firmware that is on this device, you can't really do that much. And so luckily this particular device has its firmware in an accessible format because it takes firmware updates over USB. And if you look at the file that they upload onto this device, it has what looks very clearly like an ARM Cortex-M vector table at the beginning, but that's not the only thing that's in this file. There's also some metadata in the beginning and scattered throughout this file, and unless you want to sit there guessing at what the metadata means, like what kind of checksum is this, what kind of CRC could this be, is this a length here that describes how much firmware there is before there's another blob, unless you want to guess at those kind of things, you're kind of not even able to upload new firmware to the bootloader. Right, the bootloader itself that's on there that's not contained in those firmware update images, it knows what is used to actually talk to it and to upload things onto there. And so if you have this bootloader, if you're able to get that bootloader out somehow, then you can easily go reverse engineer the code and figure out what the actual structure of that metadata is. And though I didn't actually get the bootloader out by glitching, eventually I figured out the format, was able to find another vulnerability and then get the bootloader out via some simpler exploits. This device was able to be hacked and there's tools for it. And it would have been a lot easier to do that if we had the ability to get the bootloader out almost immediately. I'm going to hand you a slide clicker now.
Oh, wow. I don't get to play with this very often.
Responsibility.
Excellent. All right. Click, click, click. Not all, but many security issues that we have come from us making assumptions and those assumptions not being valid, such as, oh, let Dominic write the code. He knows how to code. Nah, bad assumption. Things like string copy. String copy is generally known to be a pretty bad idea if you're not giving it a length field. If you use that, you have no way to know how long your input was, and it's going to just be copied all over your stack, and I hear from some hackers that that's bad. On the right-hand side here, there's a paper by Sergey and Julian about parsers, and we have this concept that if we design a file format, that two people build a parser for that very well-defined file format, that those parsers will treat things the same way. And it turns out people are very bad at coming up with unambiguous file formats, and so parsers are bad. Now, it turns out you do exactly the same thing in hardware. One of the things you do is you have to make an assumption that if in the data sheet you say, power this chip with a voltage of between this and this, you kind of have to make the assumption that that power supply is stable and that power supply is constant. And the same goes for the clock. You make this assumption that as long as the clock speed is within your valid range, everything should should work properly. And you kind of have to make this assumption that the clock is not going to go away or change dramatically, or the power is going to increase or lower dramatically. And this is where glitching comes in, because what we do is we subvert those assumptions and are able to use them to change the behavior of a part.
Right, and so we're able to secure systems usually by identifying the assumptions we make and constraining those assumptions. So we can do things like say, I'm not going to assume that the user is handing me a nice null terminated string that fits nicely in my buffer. It's a lot harder to build a chip that behaves correctly when you start pulling its power away for a period of time. It really drives up the cost of your chip. Yeah. Same thing with the clock. You start having these kind of fundamental assumptions that's really not worth coming up solutions, not worth constraining your device to necessarily have to work without power or without a stable clock. And so when you start subverting these assumptions, just like when you subvert the assumptions of someone designing software, you get all kinds of interesting and potentially exploitable behaviors.
Yeah, and I think a point you touched on, which is that there are methods for avoiding this. They absolutely exist, but they're expensive. They add complexity to the part that you're using. They add cost, and what you end up with is much more expensive microcontrollers, which then means you're not going to get your dirt cheap, I don't know, internet connected camera or whatever other like cheap IoT rubbish that you buy is going to go up in price, and the manufacturers want to use the lowest cost thing. So like the vast majority of parts that we see out there like don't have any of those kind of protections on them. Oh, I can use the slide clicker, can't I? There we go. So can I have a quick show of hands? Who knows how glitching works? Has glitched something before? I can't really see because there are huge stage lights, but I don't think that's a huge percentage of the audience. So I was in everyone else's shoes up until very recently, and so I'm going to try and give you an explanation, and then when I do it badly, Kate is going to fill in the gaps. But essentially, there are two key types that we're going to be talking about and that a lot of people use. One is clock glitching, and the other is power or voltage glitching. With clock glitching, what you do is you take this nice, wait, is one of these a laser? Mm-hmm. Well, that is almost invisible to me, so good luck to the... Okay. What you have is you have these nice clock pulses that you can see on the slides, and they... I think the way a lot of people visualize what happens inside a processor when the clock signal comes on is like everything happens as soon as that clock pulse happens. But realistically, what happens is those things happen in stages. So first of all, maybe we increment the program counter, and then we go and decode the instruction that we're pointing to, and then we work out what that's going to do, and maybe implement, is it an add? Is it
not necessarily in stages, but in parallel, we have all the intermediary pieces of those computations coming together, right? So here we can see, if we were to take a look inside the circuit, we'd see all these different pieces working kind of together, coming up with different pieces of the computation, and then finally, right before the next clock edge, or some period of time before the next clock edge, everything resolves to a stable state.
Right. Thank you. But what happens if we shorten that clock pulse and we bring the clock line back down midway through that? Can we make it so that maybe some of that computation happens, but other parts don't happen? And spoilers, the answer is yes. And so we can do things like have the instruction pointer increment, and then the result of whatever that piece of computation is doesn't go anywhere. It just doesn't happen. And then on the next pulse, the program counter is exactly where it was, but the previous instruction didn't happen. So if that previous instruction is a jump, we've now just moved over it in the code. Happy? We can move on? Excellent. This is the one that I don't know as well. Right, voltage glitching. So inside the chip are a lot of transistors. Yeah?
Is this my cue?
No. I know a little bit more. I don't do hardware. So there's a lot of transistors, and when they're stable, when they're not switching, they draw very little power. Right? Okay. Sorry that I have to keep checking it. I just don't want to get it wrong. But when they are switching, they draw a lot more power. And so the idea being that they're fairly stable. If you can make it so that when they're switching, you very briefly change the voltage that you're supplying to the chip, you have a much better chance of influencing them in a way that's unintended. So if we suddenly drop the power on a chip as it's calculating, say, the final stage of a checksum or something, is that, yeah? Then it's much more likely that those values will come out incorrectly.
Right, and so the takeaway here is that if you have a portion of the chip that is making some kind of computational change, something that's changing state, and you were to suddenly deprive the chip of the energy it needs, those pieces are much more likely to be affected by the rapid brownout, the rapid dropping of voltage, than pieces that are in a steady state.
Right, if the chip's not doing anything and you move its power supply around, it's not actually going to have that much effect. It's only the things that are changing right now. So the register, the value that it's currently writing or something like that is much more likely, or the value it's currently calculating is much more likely to change at the point that you move that power rail. I'm glad we got through that. Okay, does anyone genuinely feel more informed than they did 2 slides ago? Wow, it would be much more flattering if it wasn't my employer. So here's some pseudocode. This is just something, let's say we've got a buffer, we want to send that buffer somewhere. We have a function called sendByte, and we iterate over that buffer, sending a byte. I've written code like that on the left. I imagine many people here have. And this might be what it looks like when it's compiled. So let's say that what we really want to do is send out that buffer, but we want to subvert this system to send out everything that comes after that buffer. We want to send out the rest of RAM. Now, there are a couple of things here, a couple of steps in this program, which might be of interest to us.
Right, and before we do this, disclaimer, this is all pseudocode, so this is assembly that I wrote to be representative on a plane. I think it's a weird mix that I came up with between like a RISC processor and an 8051, because that's how it was natural to express this particular thought. But excellent. I think this is something that people who are familiar with assembly could understand.
Excellent. All right, so this is written in Temkin microarchitecture. So first up, what we do is we multiply, this works better on a black background. We do this multiply to work out the size of our list. If we could modify that in some way, we could get a length field that's way, way bigger than the length field that we're supposed to, and so therefore, so when we're comparing this length, we're going to get much more. Alternatively, every time we go around the loop, we decrement the length. If we can make this decrement fail, or happen in a strange way, we might be able to get a much bigger number loaded into the length field, and therefore, again, we get a lot read out. And the final one is this jump. If we can make that jump get skipped, then the length will already been decremented. Next time around the loop, the length will become -1, and we'll just keep decrementing the loop until we run out of, until we loop through that entire integer again.
Right, and so we have these opportunities that we can, if we're capable of corrupting values or we're capable of skipping instructions, we have these kind of windows that we can use to see things that are past that buffer in memory. And depending on the individual device and what you're sending out, that could be transmission from something that's in read-only memory, and you could get what's next after that read-only memory, which might be firmware or might be secrets. If it's in RAM, potentially you have other values that the device may not want to disclose, and we'll see in more complex cases we can actually take advantage of this to get more than just the data that's immediately following in RAM. But the key is that timing is absolutely critical. In order to be able to do this, we need to be able to, we don't necessarily know at what points exactly the device is going to be vulnerable. We can kind of guess here that it's in those instructions in red that we're likely to have the effects we want, but we don't know when during those clock cycles we might want to glitch. We don't necessarily know, what kind of glitches are going to be effective, or if any are going to be effective on a given system. So in order to do that, we need to be able to experiment. And in order to be able to experiment and have those experimental results mean anything, we really need a very precise way of identifying time as is relative to the thing that is executing the program itself.
Yeah, so this diagram just kind of shows that like this red line here, these are all the options we have to have a successful glitching attack. And it's, it's fairly spread out, but there are a lot of them. So this is the multiply. We've got one chance at that. Then this kind of decrement happens every time around the loop. And we have lots of chances to hit that one each time. And then finally we have this jump when we finish the loop. And like we only have one chance at really skipping that step as well, because there's only one time that jump is meaningful, and that's when we hit 0.
Right, and so this may seem pretty synthetic. No, go ahead, for the next slide. So this may seem pretty synthetic. That may seem like the kind of code that you'd hopefully not see in a lot of programs, depending on the use case and depending on the constraints. But this is exactly the way in hardware a DMA controller works, right? It is constantly subtracting from its length register by 1 or more. It is constantly incrementing the address that it is reading from, the address that it's sending down the bus in order to gather data. So even if that software example looked a bit synthetic, it is absolutely applicable to embedded hardware.
Yeah, and there's absolutely no error checking, because you've got a DMA controller on a microcontroller. What's it going to do when it errors?
Right, so in a lot of cases...
It can't pop me up a dialog that says, hey, something's gone wrong, or you're not writing to the right bit of memory. It's just doing what it's told. So we've done a lot of that. This isn't like a super clever attack against something or anything. This is a little Python script that Kate hacked up, which talks to the DMA controller on our GreatFet board that's connected to the system, and just allows us, all it does is take the parameters we give it and programs it into the DMA controller. And
I'm specifically an LPT 4330 microcontrollers. This is not something that you're going to see in every DMA controller, but on a lot of the embedded DMA controllers, error checking is a premium feature and is left out of a lot of the individual peripherals that use DMA. So the CPU itself may execute on the bus, execute transactions, and get notified if it requests memory that doesn't exist. A lot of times a DMA controller will have absolutely no error checking, just because there's no way to handle errors when hardware is executing them. So it won't stop transactions, it won't generate a fault, it won't generate an interrupt. It's just happy to do things like read all zeros.
Right, and so this is the thing. I just read a section of memory that I know is RAM, and I read 128 bytes out of it, and it gave it to me. But if I were to do the same thing again and read, what address do you want me to read?
Give it like 30000000.
Let you do that. But there are sections of memory that don't mean anything. They're memory mapped to I/O. There are just like reserved sections that don't exist. It doesn't error. All the DMA controller, we're just representing on screen exactly what the DMA controller is giving us back. And when it gets nothing back over the bus, it sort of says to memory, hey, I'd like to read this value. And the various peripherals, no one responds. And the DMA controller says, guess it's zeros then. And it just keeps going. And so if we can convince a DMA controller to read a section of RAM and just keep going, it will just read us zeros until it runs out, until its counter overflows. And then it'll just start again at the bottom of RAM sometimes.
Right,
and so we can just keep reading. As long as we can get the DMA controller to do the thing we want, we can get it to keep reading us out.
Right. And this is really cool, because if you actually go and ask it for an address that is all the way at the end of RAM, this particular microcontroller has a 32-bit address space. And if I say I want the absolute last byte that's in address space and 127 bytes following it, it will happily read that last byte, and then the 127 bytes it gets when it increments that last address and rolls back around to 0.
Yeah.
So this gives us almost unlimited opportunity, if we're willing to read absurd amounts of data, to explore the address space. And if we happen to, for example, corrupt a length field that's supposed to have a value of 10 and is 32 bits long, and we get something that's really, really, really long, there's chances that we're going to get things that are, after that in memory, wrapping back around and starting again.
Yeah, exactly. So if we do manage to take the 32-bit length field and glitch it to become -1, jump that comparison to 0, and get it to become -1, it will continue reading all the way around until that integer loops, which happens to be about the point that memory loops on this thing. So we get all of RAM. Describe the chip whisperer.
So one of the foundational pieces of technology we are using, we're basing a lot of our work on, is the chip whisperer. So picture it as the chip whisperer Lite, which is the inexpensive variant of Colin O'Flynn's glitching toolkit. And this is a toolkit that lets you do some power side channel analysis and some basic glitching attacks. It has modules for clock glitching and for power glitching, so we can implement both of those two kinds of attacks. And it provides software and firmware on a microcontroller and FPGA that are designed to let you precisely time glitches relative to some known synchronization point. But that synchronization point has to be specified for the chip whisperer. So the chip whisperer Lite has only the capability to synchronize to a single rising edge or a single level triggered event. So it can't go and say, I want to time this to, for example, a USB communication or to a UART communication. It can only say, tell me when something happens on the host by building your own piece of hardware and having that hardware indicate to me that something's happening.
Yeah, so what we want to do is we want to be able to tie that DMA, something that's using the DMA controller and decrementing that length value or whatever to the chip whisperer, where we want to just be able to say, yeah, go for it, glitch now. And so we want to tie those two things together, and we did. So if you look at a typical microcontroller datasheet, what you see is something along these lines. All the little boxes around the outside are peripherals that implement various protocols and things like that. We've got UARTs, we've got USB somewhere on here, we've got ADCs and DACs. This SGPIO thing up here is a high data rate thing. All these protocols that you might want to speak.
So the challenge as an attacker is if I take a device that has a lot of these buses populated, I take a board that is using USARTs and it's using a UART and it's using USB and it's using the SD port and it's connected to an eMMC card. If I want to start breaking into that device, I have to build purpose-built triggering hardware right now that is capable of identifying exactly when those individual peripherals are being used and for what. So in order to synchronize up with this, I have to go and build purpose-built pieces of hardware to test on an attack that I'm not even sure is necessarily going to work. And it would be a lot nicer to be able to, instead of having to build that purpose-built hardware, have some kind of toolkit that provides a lot of those missing pieces so that you can actually go and say, I wonder if attacking USB is going to work. Let me try USB today. Okay, this pre-made toolkit is showing me that USB seems to be a good option. 12 hours later when you've run glitches for a while, I seem to have some interesting behavior. Let me go into more depth with USB.
Yep. So this is where GlitchKit comes in. This is something that we've been working on over the past couple of months, and it ties together a lot of these features that we want to use. It ties together various different, it ties together synchronization features of. Do you want to go into this now?
We're going to talk about them in the
yeah, okay, that's good. So this is just an overall diagram of GlitchKit. We're going to go into it in detail in a second.
Yes, the idea is that this is our open source software toolkit that is designed to work with some existing open source hardware, but kind of bridges that gap and lets you go from kind of having interest in exploring a system to attacking that system as quickly as you can. You're still going to have to make some hardware modifications to your target device, but that's adding transistors and rerouting wires instead of building purpose-built hardware in order to be able to try testing those individual glitching those individual buses, and often the modifications that you make are modifications that are actually useful across all of those different buses. For example, modifying the power supplies that you can glitch its power is going to be useful no matter which one of those buses you're trying to attack with voltage glitching.
Yeah, the goal is that we're not trying to bring the amount of hardware hacking you have to do down to zero, because that's virtually impossible in this with this technology. But we're trying to take it from, I've got to spend 2 weeks designing a custom board, sending it off to a PCB fab, getting it back, building this thing with a couple parts, to a couple of hours. Okay, well, I've pulled off all the decoupling capacitors, and now I've hooked up my hardware to it. Now let's go and see if we can glitch it. So just trying to reduce that turnaround time and make it easier, especially if you don't want to have to design hardware. So what we really need is something that implements a bunch of these different peripherals and things like that. So it seems like if we're going to try and implement those, we should just find out what part this datasheet is from and build that onto a board, which turns out we already did, because we did this the other way around. And this is great fit. There's one in my hand. It's about this big. Me for scale. It is a microcontroller board that Mike Osman designed. He's some guy. It's open source hardware. It's like a breakout board to build interesting modules to sit on top of. It does various USB stuff that we've spoken about before, and you can go build one yourself right now. The designs are all on GitHub.
And so this microcontroller here, kind of the way this board wound up existing is that this was used previously in HackRF. It's a really neat microcontroller.
Yeah, we use this chip in HackRF, and I think Mike was reading the datasheet at some point. He's like, this part's really cool. I'd love to use some of the other peripherals, and I'd love to make it easier for other people to use some of these peripherals and see how and have easy access. I want to be able to plug something into my USB port, and then I want to be able to speak GPIO or SPI or something directly, and I want to be able to do all those things on a single board, and that's kind of where GreatFet came from.
And so GreatFet provides this base platform which you can build on top of to add other features. There are these add-on boards that are similar to Shields called Neighbors that theoretically add other. You shaking your head at the name?
A little bit.
Thank you, Travis Goodspeed, for that.
But I have no problem calling them neighbors. I have a problem with the fact that I spell neighbor differently to the rest of my company. So let's step through GlitchKit.
One more thing.
Oh, I'm sorry.
So when we talk about GreatFet, we are talking about both that board and other boards that are compatible with it. So if you have a radio badge because you went to CC Camp a few years ago,
2015, yep.
2015, then you already have a GreatFet, because the GreatFet software runs currently on that. And it's not the preferred form, because you can't stack those additional headers on there, but it'll work just fine for doing glitching attacks if you're willing to remap a couple of GPIO.
Right.
So,
bet you're wishing you bought camp tickets now. Anyway, so let's step through GlitchKit. There are three main kind of sections of this code. First up, we've got an event router, and the event router lets us take various things that are happening in our target hardware and combine them in interesting ways. So, we've got, you're looking really quizzical at me about this. I'm sorry. So maybe we want to, only bring up the power supply when this other thing happens, and we want to fiddle with the clock in some way when this GPIO line goes high. And we are able to kind of connect those events and make more complicated structures of the hardware state.
Right. So a common kind of task when you're using these devices, when you're trying to glitch devices, is to get things synchronized across a variety of tasks. So you might, let's say, be attacking a USB device where you need to apply power and then wait for the system to boot, wait for it to show you that the microcontroller on board has started up. And then at that point, you're ready to apply some stimulus in order to generate an attack. Or you might have a device that you need to power up and then immediately provide a clock which is going to drive that device, but you don't want to provide that clock before power is on, otherwise you're driving current into a chip that has no VCC, has no supply rail. So this event routing system is kind of the heart of GlitchKit, and it lets you take all these different pieces of information, all these pieces of stimulus, and use them to drive things like, all right, when VCC turns on for the target board, I also want to start a clock, and then I want to wait for the system to appear to boot by monitoring one of its GPIO and seeing when that goes high. And then finally, when that happens, I want to throw some stimulus at it, and then finally, when that stimulus has taken, I want to trigger a glitch. So that event routing system is what connects all those individual pieces.
Yep.
We also have a clock management section, which is which handles things like making sure that all the individual pieces of your system share a common clock when you can. Because it's a lot easier to get everything synchronized up if they're all executing on the same time base. So the clock management will take in an external clock and allow the GlitchKit hardware, the GreatFet itself, to execute on the same clock as either your target or as the chip whisperer. And so you can get all of the chip whisperer and the GreatFet pieces of that stack synchronized up.
Yep.
And it'll also provide clocks to things that are better off being given an external clock. So it can then go and apply clocks and theoretically in the future modify those clocks for clock glitchings if you're using this particular path. So it gives you the ability to buffer clocks and spread them out throughout a system without having to necessarily build purpose-built hardware in order to ensure that the clock is stable as it's being distributed.
Right. I guess the short way of saying that, if you're going to do things that require like incredibly tight timing, it's useful to be running from the same time. So we can have the chip whisperer board and the GreatFet and whatever our target device that we're trying to glitch all running from the same clock. So they're kind of running in lockstep with each other, so that we know if we're trying to if we've got a time offset between the start and when we do that voltage glitch, we know that's consistent across the boards. So the other thing you might want to do, a lot of glitching kind of to try and get the bootloader or something might happen or doing something weird to the bootloader might happen super early on. You might turn on the chip and then immediately try and do something after a short couple of instruction delay or something. But sometimes you want to probe the hardware in some way. You want it to boot up normally, and then you want to modify it in some method, some style. And so we can act as a USB host and a USB device and sometime in the future a flash chip or an eMMC device. And so the idea being, maybe the thing that I think is actually going to be the request to the device that I want to glitch is like some USB command that has to happen after we've enumerated the device. So we've got like 5 or 6 USB commands that need to go between the host and the device before I can start sending it this command and then trying to glitch it during that command. And so what we're able to do is we're able to bring up the device, enumerate it, get it into the right state, send it that command, and then immediately tell the chip whisperer, hey, now's your time to start glitching.
Right, so this gives you the ability to do really precisely timed stimulation of that device. So if you think that a vulnerable piece of code or a vulnerable hardware function is only ever exercised once you've received a certain command, let's say, I'm a USB device, I have the capability to self-describe, I'm only going to do that when you ask for a descriptor, you need to be able to go and start poking that device and prodding it in order to get it into a state where it's doing the tests that you think are vulnerable. And while you're doing that, you often want to know what stimulus are being applied and where they are in time, because sometimes the stimulus for triggering is I've just asked it to respond to a given command. So all of these stimulus modules both exist and to move the device through a given device into a given state, and exist so that they can provide inputs to the event routing system, so you can do things like, say, turn on USB VBus and then send a command and use those as inputs for, both for glitching and triggering glitching, and for generating other events like turning on clocks.
Yeah. So by extending by allowing us to kind of interact with the device for longer and do more to change the state of the device before we try and attack it, we massively increase the attack surface, because we're not just going for a small subset of the code that's running on a device. We can start to play around with all sorts of weird arbitrary USB functionality of this thing, because you don't know which part of it is going to be the most susceptible. And there's a fair chance that the descriptor stuff might be really solidly written. It might even be implemented in hardware on the peripheral. But those USB vendor requests that someone's thrown together to the day before they have to ship this piece of hardware, they might be written in that slightly more sketchy style of let's just decrement an integer and see what happens.
Or there might be more than one thing going on in the hardware as a descriptor is sent out, and that makes it very difficult to glitch, because if you start glitching the descriptor request, you might also knock out something that is responsible for the core functionality of the device, and the device's memory bus may go down, right? Yeah. So being able to explore a lot of that is really important. Also worth noting, I think this is probably the first pitch you've heard today where we tell you that a project massively increases attack surface. So that's an A+ feature.
Vendor pitch. Increasing your attack surfaces. Okay, so trigger feature. This is kind of where this, I guess, all came from originally. Is that one of the things we wanted to do was be able to have these kind of more complex methods for deciding. Okay, well. So for example, the simple event trigger here, what it does is it allows us to hook into a bunch of I/O lines on the target device and say, well, when this thing happens 5 times and these 2 lines are high and this line pulses, that's when you trigger. And so this is kind of fun, because you can just hook up to a spy chip and you can say, well, I know this thing's going to read 4 times when it starts up, and then what I want to do is try and glitch it right after it does the 4th read. And so all you do is you hook up to the enable line and you say, well, when that one's pulsed 4 times, that's when you trigger. Or you had a more complex example than that.
The simple event triggers let you take a variety of just general Boolean conditions for input pins and build complex conditionals out of them. So common example, and I think the more complex thing that I was talking before is, I might have a microcontroller that reads some information off an external flash, and I might want to know where it is in that read. And I could go and build a whole SPI peripheral and kind of fake an SPI flash chip and know that by emulating that SPI flash chip, I get this insight. Or I could say, okay, I know that this thing behaves the same way every time. The 4th thing it reads is always that piece of information that I'm interested in using as my time base. So let me just say, okay, the 24th clock edge here, or the 30-second clock edge here, while the chip enable pin is low, happens to be the thing that I'm interested in triggering on. And this doesn't necessarily have to be the thing that generates that final glitch trigger. This can be the thing that prompts you to, let's say, turn on the system's clock, turn on the clock to another target device, or you can use that as time base to start executing some stimulus. So when it gets to this point, that's when I want to start sending it USB packets.
Yeah, and to a certain extent, you might want to do that because you might want to apply power to the device and then wait for it to come up before you start trying to talk to it over USB and things like that. And so you might just wait for example, like those I/O lines don't have to be like complex chip-to-chip interfaces. You can just hook into one of the LEDs and say, well, when this LED comes on, I know it's booted. Something like that. UART, I don't really want to talk about UART because I implemented it and it currently doesn't compile. But UART is, I mean, it's not surprising. UART is like a pretty common kind of debug interface that you're going to find, like if you just tear open one of those like standard routers that you get from your ISP, like that thing's got going to have a serial connection on it, and so you might want to use that to work out when its bootloader has started up or something like that, because it will dump some information. And then these things can be used. The final thing is to then talk to the chip whisperer and trigger some output from it. So
this is a cool thing because you can take that trigger signal and you can trigger the chip whisperer to start doing its glitching process. Or if you want to, you can use that to drive the trigger input to your oscilloscope or logic analyzer. So you can use this as a source of debug information outside of glitching, even though that's not our main purpose. So really, this is a general purpose stimulus and triggering engine that we happen to be using for glitching. So one of the kind of pieces of work that happened a couple of years ago before where we are now, that was kind of really inspiring for this, was done by my friend Micah, who wanted to be able to take a USB tablet that she had and use it as kind of a general code execution engine to prove out an idea that she had, which was that these things are an awful lot like RFID readers. And she kind of had the idea that she wanted to be able to take this, run her own firmware on it, and be able to read an RFID token that was held really close to the actual switching matrix of this Wacom tablet. So this is the kind of thing that you normally use with an inductive drawing pen, the kind of thing where the pen has no battery, but by holding it close to the tablet, it's able to receive power, modulate its load on that switching matrix, and thus kind of communicate a little bit of information like, yes, I'm a pen, I'm being pressed this hard. And that kind of functionally looks a lot like an RFID chip, which also does kind of a load modulation. So whereas the pen was receiving power and then loading the power lines more or less in order to communicate where it was on a grid and communicate how hard the nib was being pressed, an RFID takes power and then just transmits back via that load modulation a simple fixed ID. And so she had kind of the idea that those things could be, those are basically the same pieces of hardware, just the pen in this case was a little bit more complex. And so she wanted to be able to get some firmware execution on this device. But looking at it, she found that it had a custom microcontroller called an LC87, which was a completely custom architecture by Sanyo or onsemi, and it had a debug interface exposed and on that was completely undocumented. So she wasn't able to extract the firmware in any easy way. So what she did, because she's a really good thing, yeah. What she did, because she's super devoted and really loves getting in depth with these kind of things, is she decided to try to extract the firmware by taking advantage of the way USB packets are sent and trying some voltage glitching techniques. So if you look at the way a USB control request is sent, it happens in a few stages. First, you send it a command in a stage that's called the setup stage, which can contain the standard USB commands that force compliant devices to describe themselves. So like a get descriptor request will make a USB device respond with some descriptor describing its own functionality. So when you plug in a USB device and it says, hello, yes, I'm a Wacom tablet, your operating system knows that because it asks the device first for its device descriptor, which contains a vendor ID and a product ID, and a couple of string descriptors that contain that string. Yes, I'm a Wacom tablet, I'm a CTE 450. And in order to be a compliant device, every device has to be able to do some amount of self-description. And the way that's usually executed is by taking small pieces of data that are usually either in RAM or in read-only memory and just DMAing them right out of the device. So here we have a get descriptor request that's executing. It has a single packet that is transmitted back in response, and then we have an acknowledgement that packet was indeed received. So we have the host sending get data, please, give me that descriptor. We have the descriptor being transmitted in response, and the host says, yes, I got this. Theoretically, it doesn't have to be one packet in the center. If the device decides to respond with a very, very long packet, that could also theoretically be valid. So there might be multiple packets that make up a longer transaction. So let's say you want to send 512 bytes on a bus that has a maximum packet length of 64. That could be packetized and broken up into a lot of sequential packets. If you look at the way a USB device works, it's often very similar to a host controller in that it has a linked list that contains basically an amount of bytes to transfer, and then pointers in memory to the pages that contain the data that you want to send. So really you have a length and an address here. And if we look at the way a get descriptor request might work for a long descriptor, you could have the device essentially populating a little DMA descriptor that says, I want to send 256 bytes, and they start at address hex 1000. And the device is going to start doing that. It's going to send out a single packet of length 64, because it's the most you can fit on this particular bus. The most you can fit in a single packet on this particular bus, rather. It's going to decrement the length and increment the address. This looks a lot like the example we provided in the beginning. It's going to keep doing that until it gets to the point where the length field reaches 0. And USB is almost a null-terminated kind of protocol in that when it finishes a transfer, it indicates that by sending a packet that is shorter than the maximum length. So in this case, it sent all maximum length packets until it was done, so it has to send a 0 length packet in order to indicate that it is indeed complete. Now, if we're able to start applying voltage glitching or clock glitching, if we're able to glitch something in the system and corrupt that length, then what we'll get, instead of those nice orderly transaction where we send 4 individual packets to let's say, send out that configuration descriptor, is we'll get a length that is potentially much larger, which continues to transmit and transmit and transmit well beyond when the device should have stopped. And if you have a device with a DMA controller that works like most of them do on microcontrollers, it will continue not just out of that descriptor's location in RAM or ROM, but continue throughout the entire memory map until that length field is brought down to 0. And so in order to be able to do that kind of glitching to the system, you really need a way to be able to synchronize with the system and provide the stimulus. So Micah built a custom piece of hardware called the Face Whisper, named because its use of the chip whisper technology and its descent from chip whisper technology, and its inspiration in the Face Dancer project. And this particular board contains a microcontroller, which happens to be the same one that is on a chip whisper, and a USB host chip, which happens to be the same one that is on a Face Dancer, and then some clock buffering hardware. And all that it does is, with very precise timing, synchronize itself up to a particular point in the tablet's execution, tablet microcontroller's program execution, and then send it some USB packets and simultaneously trigger the chip whisperer to start executing glitches. So in doing that, she was able to actually steal the firmware from this microcontroller, and using that, she was able to find vulnerabilities in the firmware and eventually prove out that indeed you could read RFID tokens using a USB tablet as long as they were pressed exactly against the tablet. And so this was very cool, both because it showed a novel way of getting firmware out of the device, and because it was a really ingenious solution to get at something that was a whole bunch of steps away from what she initially wanted. So she's the kind of person who has that kind of like hyper-focus and dedication to say, oh, I'd like to see what the firmware is in this. Let me build an entire piece of purpose-built hardware, firmware, and everything you need in order to be able to get the firmware out of a tablet so they can then go and look for vulnerabilities.
So I feel, having said all that, I do feel slightly bad about the next slide, which is we've essentially taken her idea and tried to make it easier. And so, bear in mind, GlitchKit and all this stuff that didn't exist when she did this, and she went and designed a board, built a board, attached it, glitched the thing, got the firmware out, worked out vulnerabilities. So now we can implement that in this Python code.
And so one of the conversations that Mike and I had afterwards was just so both of us really love making technology accessible to people.
Right.
And so one of the purposes of this, and one of the things I kind of promised Micah when I started doing this, is that we would take this whole technique, which required a custom piece of hardware and required a whole lot of different levels of understanding and a whole lot of development in order to test on an idea and make it into something that you could apply kind of relatively easily. So here's the back-end code for applying the same things with GlitchKit. This is written in Python.
We were going to go through this, but I think we're running low on time, and I want to get the demo done. We're happy to explain this at some point, but possibly not now, just because we only got 5 to 10 minutes.
The important part is that you don't actually even have to write this code, because the final form of GlitchKit has fancy GUIs that sit there right in ChipWhisperer. So if you want to apply the USB attack that Micah did, you can start configuring that right from the GUI of ChipWhisperer. So, demo time first.
Oh, okay.
Our first demo, I just show off the ChipWhisperer GUI, and then we'll talk about our work.
So this is the ChipWhisperer GUI. We now have added these various GlitchKit methods, so they'll talk to a GreatFET. So there's a big mess of wires and connectors and things on the table here, but essentially we have a GreatFET and a ChipWhisperer hooked up to our target GreatFET.
Right, and so the process of configuring this really, you go and you select, instead of the type of target that you want to select directly, you say, okay, I would like to talk to the GreatFET that's running a USB stack, so I'll select GlitchKit USB, and then from the UI you can immediately configure, yes, I'd like to read a device descriptor, I'd like to have that device descriptor be read immediately when certain pins go high, right? Yeah, so you can start building everything you need to
allow you to walk the interface you wrote it.
I don't think it's kind of difficult to see on the board, but if you look over here, here's all the configuration settings you would use to, these are preconditions that determine when an individual USB event is generated up here on the side.
So you can go into this interface now and you say, when this GPIO pin goes high, then and this one goes low, and this one happens on the 4th time or whatever, and those complex conditions that we're talking about, you can just have at that point, the software will then set trigger the ChipWhisperer to do its thing.
Right. So naturally, we're not content with just reproducing other people's work. We wanted to try doing some cool things of our own. So at some point, we had to turn against our own creation, right? And so here is a GreatFET that has been kind of actually sloppily modified, so that I promised the board had all the flux on it before we made modifications. But I've yanked every one of the decoupling capacitors rather roughly off this device, tried to make it easier to start depriving the device of power. I've added a couple of pretty nasty bodge wires here. One that connects the VCC rail to a couple of SMA connectors, so that you can do things like inject voltage in, or inject glitching signals in, pull the voltage down to 0, and because we still want some decoupling, I have a decoupling network here that is replacing all the decoupling capacitors on the board, and that is connected via a small impedance so that we can pull the device really readily to 0, but it can recharge the VCC bus from these capacitors via that small, in this case, approximately 10 ohm resistor. And so, sorry to Mike Osman, because we totally destroyed this thing that he's created, or I totally destroyed this PCB that he created. But more importantly, I'm sorry to everyone else, because look at this thing. I actually tweeted this picture, and it got a significant number of likes and retweets, and then I got a couple of people being like, clean your PCB, please.
Yeah. It's not about how clean it is, it's about the glitching.
Mm-hmm. And this actual modification was done after a couple of drinks, on the night of Christmas, which is the perfect time to start glitching new targets.
Yeah. The great thing about this is we're now able to glitch this board, and we might even be able to get the firmware off it. But there's some problems with that. One is that it's open source, so we already have the firmware because we wrote it. But also, it turns out the manufacturer of this board is incredibly litigious, and he sends out cease and desist letters when people try and reverse engineer his devices. He sometimes writes them in Sharpie, but you never know. He might.
Right. So because because one, we already have the source code to this, and it's on GitHub, and that doesn't make it a particularly interesting reverse engineering target. And two, because we're terribly afraid of litigation, we decided instead of attacking the GreatFET software that we're running on the application processor, that we would attack the bootloader that is sitting in ROM on the LPC 4300 series microcontrollers.
Yeah, the LPC 4300 series have a USB DFU bootloader and also some other USB functionality, which is sat in ROM, and there's only one ROM section here, which I can't laser point to, but You probably do.
Right, so that this device has a USB bootloader that does all the same things as that tablet because it's compliant to the USB standard. So it can do things like respond to a get device descriptor request. And so we started applying the same kind of glitching attacks to the ROM. And you might be kind of saying, well, why is it interesting to attack this ROM? One is that on a bunch of these devices, it runs from this shadow area that is at the start of RAM, because the Cortex-M microcontroller wants its vector table to be located at address 0. So it's very low in RAM. Everything that's interesting follows it, including on-device parts with flash, the contents of flash over here. And also, because if you look at the secure mode parts, one of the things that they do inside this bootloader is read encrypted images from things like flash chips, decrypt them, and stick them in SRAM immediately following the shadow area from which it's running. So if we're capable of doing glitches...
So if we can read out from the shadow area, we can continue reading, doing that DMA trick to continue reading into SRAM and pull out that now decrypted firmware from secure parts. We only have 5 minutes left, so I think we should go ahead. I do not know how to steer this GUI as well as you do, so I'm going to let you do this.
This is the hard part.
All right. See? That's what happens when you run it on my machine.
I can reset the grave hit. This is tragic.
If in doubt, turn it off and on
I have
again.
to wait for it to connect and start blinking. But here I am impatient, wanting to just click the button immediately. This is actually the hard part. So let's clear the output table from previous runs. Essentially, this is issuing USB requests to the device and capturing the response. Because we have limited time, I haven't told it what's a good response and what's a bad response, so it's telling me every one of these responses has failed. But realistically, if you expand that dialog so that we can see what's happening there, scroll all the way down to the initial ones. It's worth mentioning that this is actually a simulacrum of the device running the way it normally would. Normally when you're glitching, you would actually step through lots of intervals in order to find the few glitches that work. So because we don't have several hours to do this glitching attack, this is actually, the code has been slightly modified to, instead of always reading the correct descriptor, it jumps to different points in the glitching stack that we've found happen to work for this particular device.
So what you'll see here is we get a lot of responses that are the standard response. They're what we expect to come out of it. It's trying to read 18 bytes, that's hex 12, of USB descriptor. It reads 18 bytes, it gets 18 bytes. But this one here, it appears to have got significantly more data. And so on a previous run earlier today, as Kate said, this is simulated because it is not as quick as that when you actually run it. On a previous run, we dumped this to hex, and somewhere, can anyone see that? Anyone read that at all?
So
I'm just got to turn up my font size.
that would be appreciated, I think.
So what you can see here is what we were able to read out of that file what we were able to dump to this file was just all the memory we were able to read from the USB descriptor location onwards. And we were kind of going through it, looking at it earlier, and we're like, well, we haven't had a chance to analyze it yet. And then what we found was over here, see, it says USB-C, and under here it says USB-S.
And those are incredibly telling strings. If you've designed USB systems before, this is a USB command that's sent. It's actually a SCSI command sent over USB that's used in USB bulk-only storage. And this is the token that precedes a response of status when one of those commands is executed. So this significantly suggests that this ROM bootloader happens to have inside of it some USB mass storage functionality.
And our first response was, that's weird, we didn't think this had USB mass storage. And then we went back to the datasheet and reread it, and it does. And it turns out we've dumped the code of some ROM functions that we didn't even know were in the chip. So we were able to pull out NXP's ROM code for the LPC 4300 series, and obviously you'll be able to go ahead and analyze this. And
that's not particularly novel, because you could grab that out with GDB as well. But
yeah, it's not the most novel.
But if you were to continue doing this work, one of the theories that we have is that we didn't let this go for that long. We didn't capture that much data. I don't have any secure mode chips on me, but the theory is that after this kind of thing, the SRAM you would grab would have theoretically a decrypted firmware image if it was sent a firmware image over USB. So you could kind of use this as an oracle to take encrypted firmware images and generate the decrypted ones.
We're now, unfortunately, completely out of time. Just been told we have to go. So we will take questions outside, and if anyone has any questions, we'll be outside kind of
and if you're an
somewhere
internet viewer
towards
on the internet, our Twitter handles at the beginning.
Our Twitter handles at the beginning, or just find us. There's a great IRC channel on Freenode if you want to ask questions there. And thank you very much for listening.
And this is the URL for the project if you want to download and contribute. So thanks so much for listening.
Yeah.
Appreciate it.